In this problem, we're going to find the coordinates of the stationary points. Now, coordinates are an x and y pair, and the stationary points are points of a function where the slope is going to be 0. And what we've got to do then is find the nature of each stationary point. So the first thing we're going to do is we're going to rewrite this function so the powers are visible and they're not in the denominator of a fraction. And then we're going to use the power rule to find the derivative. Multiply times the exponent and then bring down the exponent by 1. And then multiply by the exponent. So that's going to be 9 halves. And then bring that down. That'll be negative 3 halves. Alright, so this is our derivative, and what we can do is we can make it equal to 0 because we know that a stationary point, the derivative, the slope must be 0. And so now what we're going to do is we're going to rewrite this so the powers are not negative. And now I can go ahead and solve this, and my first step is probably going to be to add 9 over 2 square root of x to the third on both sides. And then I've got two fractions that are equal to each other, so then I'm just probably going to cross multiply here. And so that's going to be 18 square root of x times 2 square root of x to the third. I'm going to divide both sides by 2, so that's going to give me 9 square root of x is equal to x to the third. Then I'm going to square both sides, and that's going to give me 81x is equal to x to the third. Divide both sides by x. And that's going to give me 81 is equal to x squared, and so then x is going to equal plus or minus 9. So now what we've got to do is we've got the x values for our stationary points, and we've got to find the y values that match up with them. So this is kind of important to remember. We're going to use the original function. When we're trying to find or use slopes, we're going to use a derivative. Either they're going to give you the slope or you're going to have to find the slope. If I have points or I need to find part of a point, then I'm going to use the original function. In this case, I've got an x and I need a y that goes with it. So what I'm going to do then is plug the 9 into the original function wherever it says x, and then that'll tell me what y is equaling when x equals 9. In this case, I'll find out that y is going to be 6. So the point is going to be 9, 6. And then when I do this for the other one, I'll realize that I'm going to take the square root of negative 9, and that's not possible, at least at this point in your math career, and so we're not going to worry about that. So the only possible point is 9, 6. We defined its nature. What we're going to do is do the second derivative, which basically means we're going to take the first derivative and then find the derivative of that. If it's a maximum, minimum, or point of inflection, the second derivative will tell us. If it's the second derivative ends up being positive, it's a minimum, and if it's negative, it's going to end up being a maximum. And if it's equal to 0, well, then we've got to do something else to figure out if it's a point of inflection. At this stage in the game, it's probably not going to happen very often where you find points of inflection, so we'll talk about that later. Anyway, I'm just going to use the power rule. I'm going to get negative 1/4 x to the negative 3 halves plus 27 over 4 x to the negative 5 halves. My point is still 9, 6, and the x part of that is 9. So all I'm going to do is take my 9 and replace the x's in my second derivative with 9 and find out what it equals. Sometimes you don't have to even really find out, because keep in mind, we don't care what it equals. All we care about is whether it's equal positive or negative or 0. So in this case, I'm going to go ahead and plug it in using the calculator. And I'm going to find out that when the second derivative, the x is equal to 9, that the second derivative is positive. In this case, 1 over 54. And like I said, I don't really care what it is. I just want to know if it's positive or negative, because that tells me what basically the graph is going to do immediately after this point. If it's positive, it's going to go up, which would make it a minimum point. And if you want to validate this, what we'll do is we'll go to Desmos, and here you see how I've plugged in the original function. There's 0.96, and you can see how this is clearly the minimum point, or at least if there is a minimum point, you can see why this might be it. So I hope that helps. Thanks for watching.